In this video, we're going to cover some very common practice problems on energy conservation. So in the first 2 to 3 minutes, we will learn or review, if you have watched my first video, a method for solving energy conservation problems. That is a step-by-step instruction on how to approach any kind of problem that has to do with energy conservation. This will especially help to someone who is lost how to approach or even start these problems, because it will give you a roadmap to, no matter what the question is asking, you will know what steps you need to complete in order to solve that question. In order to practice these questions, we'll look at one roller coaster example, and we'll look at another second example of kinetic and potential energy. So let's firstly start by examining the method for dealing with these kinds of problems. So remember, our fundamental law is that the initial energy is equal to final energy, right? So the first step, therefore, is to sketch the problem and define what are those initial and final moments in question. Then at both initial and final moments, you want to ask the following questions. Does this object have velocity? If it has velocity, it has kinetic energy. Does the object have height? If so, it has potential energy, right? If not, it doesn't have potential energy. Is there a spring that is being compressed? If there is, then it has potential energy. So at any of these initial moments, right, it can have one energy, right? Let's say kinetic energy, or it can have two different types of energies. Let's say both kinetic and potential, right? Now, rarely we'll have three, but anything is possible. Then you simply set the sum of all types of energies equal to each other. So you set all the initial energies equal to all the final energies, and just plug in the formulas for for kinetic energy, which is 1/2 mv squared. It should be on your formula sheet. For potential energy, mgh, or for elastic potential energy, 1/2 k delta x squared. So you plug in the formulas and you solve for the unknown. So a pretty simple 3-step process. Let's take a look how this process applies to solving the following problem. So here we have a roller coaster. This is a very common problem in physics classes, right? So consider a roller coaster with a mass of 1,000 kilograms that is traveling at a velocity, so at a 10 meters per second, at a velocity of 10 meters per second as it crosses point A, which is located 20 meters above the ground level. If there is no friction, determine the following. So the first question is asking you to determine the velocity at point B, right? So let's go through our first step. What is the initial and what is the final moments in question? What do you think? Well, it would make sense to make this is our initial moment, right? At A, and our final moment as B, because our initial moment, right, because at A we know all the information, and at B is what we have to solve for. So let's say our energy at A equal to energy at B. So the next step is, let's ask what kind of energies does it have, does this roller coaster have at A? So does it have velocity? Well, yeah, we are given some velocity in the problem, so therefore at A it will have kinetic energy. Does it have height above the ground? Well, yes, it does. This height above the ground is 20 meters, so it will also have potential energy. What about point B? Does it have kinetic energy? Well, definitely, right? Because it's asking us about the velocity. So if it's asking if it has a velocity, it needs to have kinetic energy. What about potential energy? Does it have height above the ground? Well, no, this point B is basically on the ground right here, so it does not have any potential energy. Okay, so once we did this, let's plug in for the formulas of each. So 1/2 mass times velocity at A plus formula for potential energy is mgh, so height at h, and formula for kinetic once again is 1/2 mv squared. But of course these velocities are different, right? Velocity at A is not equal to velocity at B. So we're trying to solve for velocity at B. So let's see, why don't we just multiply, we can plug in all the numbers now. So 1/2, let's see, there is mass in each term, so just to simplify it, right, I can cancel it out. And I have the following equation. So 1/2, velocity at A was 10, so 10 squared plus g, let me just take g as 10. Height of A will be 20, right? 1/2 VB squared. So 1/2 of 10 squared is 100. 1/2 of 100 is 50 meters, plus 200 is equal to 1/2 of VB. The rest is just going to be algebra. So I multiply both sides by 2 and take a square root of both sides to find the velocity at point B. So square root of 500 is going to be 22.4 meters per second. Great. So now you can actually try the second part on your own now that you know how to approach this problem, right? Now we need to find the velocity of the roller coaster at point C. So let's take a look how we would solve this. So again, we can select any point as our initial, and as our final point, it would make sense to select point C, right? Because we need to calculate for it. So we can select actually our initial moment either as A or B. I think selecting it as B might be a little bit simpler because there's only kinetic energy at B, right? So we can select energy at B equal to energy at C, because all of these energies, right, are going to be equal to each other, again, due to conservation of energy. So therefore, energy at B is equal to energy at C. So again, what type of energy does it have at B? Does it have velocity? Yes, so it has kinetic energy. Does it have height? No, therefore there's no potential energy, so it's just the kinetic. What about a point C, right? What type of energy does it have? Does it have velocity? Well, yes, because we're asked to find the velocity, right? So if it has velocity, it will have kinetic energy. Does it have height? So it does have height, therefore it has potential energy at C as well. So let's plug in our formulas, 1/2 mv squared for kinetic energy and mgh, right, for potential energy. Great. Again, just like in the previous example, we can cancel out the mass everywhere. So let's see, we're solving for velocity at C. So let me rearrange this equation. So I'm going to subtract gh from both sides, right, to cancel this out. So minus GHC is equal to 1/2 VC squared. Now I'm going to multiply both sides by 2, minus 2HC. Now I'm going to take a square root of both sides and plug in all the numbers that I know, right? So V of B, the velocity at point B was 22.4 squared, minus 2 times G as 9.8, and the height as 15. So I get velocity of C is 14.2 meters per second. You know, I'm great at mental math, right? So this is our velocity at C. So a very similar approach, right? Again, you select energy at one point equal to energy at another point. Then you find out what types of energies it has at each of those points, and plug in all the known values to calculate for the unknown. Great. Now let's solve the third one. The third part to this is talking about when, let's say, your roller coaster now is brought to a halt by a spring mechanism with a spring constant of 1,000 newtons per meter. Calculate the compression of the spring. So essentially what they're saying, right, is that now there's this point, let's say D, right, where the spring is being compressed and the object stops. So let's take a look. Again, we can say that energy at A, right, is equal to energy at B is equal to energy at C is equal to energy at D. So energies at all of these points, including when the roller coaster is being stopped all the way by a spring, are equal to each other. So we can set any two energies equal to each other. But let's say, again, I like point B. So why don't we set energy at B equal to energy at D? So that would be our third step right here. So energy at B is equal to energy at D. Now, let me bring back the picture. As you remember, the energy at point B, right, was only kinetic energy. At D, right, let's ask ourselves, right, is there velocity? Well, no, because that's when the cart is being stopped. Is there, so therefore there's no kinetic energy. Is there height? No, because, right, it's on the ground. Is there elastic potential energy? Finally, the answer to that question is yes, right, because there is a spring that is being compressed. So energy of the spring, right, is going to be here. And at B, as we said, is just the kinetic energy. Great. So now let's take a look at our expression, right? So here's the elastic potential energy. Let's plug in our formulas. 1/2 mv squared for kinetic energy, 1/2 k delta x squared for elastic potential energy. 1/2 cancels out, and we can rearrange this for delta x. So I can divide both sides by k, and I can take a square root of both sides to find delta x. So square root of mass is 1,000 kilograms from the previous picture. Velocity at point B was 22.4. And k, the spring constant in the question, it was given as 1,000, right? So if you calculate this, you will have 4.73 meters. So now we have became the designers of roller coasters, right? You can put that on your resume. Now, let's take a look at one last very quick problem that will demonstrate another application of potential and kinetic energy. So this one, determine the maximum height reached by a 10 kilogram block that is initially being pushed up a frictionless inclined plane at a velocity of 5 meters per second. The inclined plane is at 30-degree angle relative to horizontal. Calculate the height at which the block comes to a stop. So don't be scared by the incline part of this, right? Because this is actually going to be a pretty fast problem. So let's say here is your initial point. Again, first you would draw a sketch, of course, as always. So your initial point is when you basically are pushing the box, right? And your final point is when this box comes to a rest at the top of the incline. So let's ask our three questions, right? At our initial point, does it have velocity? Well, of course, right? Because it's being pushed with a certain velocity, so it will have kinetic energy. Does it have height? No, because it starts from the ground level, therefore no potential energy. And of course, no spring energy because there's no spring in this question. Finally, final point, right? Does it have velocity? No, because it says block comes to a stop, meaning there's no velocity. So no kinetic energy. Does it have potential energy? Of course, because it reaches a certain height, right? And again, there is no spring energy. So initial energy equal to final energy. Initially, the energy is just the kinetic one. Final energy is just the potential one. Kinetic energy is 1/2 mv squared formula, and formula for potential energy is mgh. Right? So we can divide both sides by g and find the total height as simply 5 squared over 2 times 10. I'll use 10 for g as 1.25 meters. Great. So this is our final answer for this problem. So as you see, inclined planes aren't always scary. In the next video, we'll look over two really important examples of how energy conservation applies to problems related to springs. So keep practicing, keep watching these videos, and doing the problems yourself on your way to an A. Thank you, guys.